I'm Sangeeta Sadwal, and today we are going to study Chapter 2, the colligative properties of solution. We specifically dealing with the relative lowering of vapor pressure in today's series. We already know that solutions are the special types of homogeneous mixtures which are composed of two or more substances. And in each of this mixture, a solute is a substance which is dissolved in another substance. The solute is in lesser quantity, whereas the solvent is in more quantity. For example, the mixture of salt and water is considered as a salt solution. Whenever the solutions have two components, the solution is considered to be a binary solution. The component which is in more quantity is called as the solvent, whereas which is in the less quantity is called as the solute. So we can easily see that the solvent particle and the solute particle are homogeneously mixed together. Before going further, let us come to understand some of the basic concepts. Electrolyte. The electrolyte is that substance which, when dissolved in a solvent, can dissociate into ions. Thus, it actually separates into cations and anions and hence makes the solution conductive. The non-electrolytes are those substances which may dissolve but do not dissociate into ions. And one of the foremost example is glucose. It readily dissolves in water but does not dissociate into ion. So that would be considered as a non-electrolyte or a non-electrolyte solute. The third component that you should know is the vapor pressure of a solution. It is that pressure which is caused by evaporation of all the liquids. And we are all aware that all the liquids evaporate to a certain extent. They actually depend upon the surface area of the liquid, its intermolecular forces between the components, and the temperature at which that liquid is kept. So, the vapor pressure of the molecules for a solution is different at different temperatures. Thus, we can make a conclusion that solutions have different properties than either of the solutes or the solvent whenever we convert it into a solution. These properties can be divided into two main categories: the colligative properties, which depend only on the number of dissolved particles. The particles can be molecules, ions, they can be small or large, but it does not depend upon its identity. Whereas the non-colligative properties depend upon the identity of the dissolved species. Thus, in this chapter, we are going to specifically deal with the colligative properties of a solution, which are depending upon the concentration of the solute. And we are already aware of that concentration of the solute can be measured in the terms of molarity, molality, mole fraction, and that would constitute the basic component in the numericals. Colligative properties that would be included in this whole chapter would be lowering of the vapor pressure, elevation in the boiling point, depression of the freezing point, and the osmotic pressure. These all properties actually depend only on the number of particles and not on specific type of component used as a solute. We will be studying lowering of vapor pressure as a specific topic today. Whenever we add a non-volatile solute in a solvent, the vapor pressure is lowered. Just now I explained to you that each of the solution actually has a vapor pressure and it actually depends upon its surface area. So when a non-volatile solute is added, the surface is now occupied with a non-volatile solute. Thus, the molecules which were escaping into the atmosphere, which were only of the solvent, now are replaced by some of the solute molecules which do not have any vapor pressure. So here you can see that on the left hand side, the pure solvent has maximum number of solvent molecules vaporized, whereas on the right hand side you can see that because of the presence of solute, the solvent particles have reduced. This is called as the relative lowering of the vapor pressure. Now our concern is that do all the solute play the same role? So let us quickly study. Now when a non-volatile solute is added, This is due to the decrease in surface area that the vapor pressure of the resulting solution is lower. Thus, the Raoult's law has found a basic concept for finding out the volatile and non-volatile solute. Raoult's law states that a solvent's particle vapor pressure in a solution is equal to the vapor pressure of the pure solvent multiplied by its fraction. That can be mathematically formed and calculated as P of solution is equal to xi solvent P naught of a solvent. Here P refers to the vapor pressure of the solution, xi represents the mole fraction of the solvent, and P naught refers to the vapor pressure of the pure solvent. Let us first of all consider the solution where liquid and liquid have been mixed together. For example, alcohol and water. In this such type of a solution, the volatile liquid A and B are in a container. Because both of them are volatile, both of them would be actually forming vapors. Hence, both of them will actually exert the partial pressure. In order to calculate the pressure of such type of solutions, we will have to take the consideration of both the components. Hence, our equation form in this case would read out to be PA is equal to xi A into PA naught, PB is equal to xi B into PB naught, which can be calculated as the total vapor pressure comes out to be PA plus PB. Hence, the xi A comes out to be moles of A divided by total number of moles. Let us take an example. Suppose you have a mixture of 2 moles of methanol and 1 mole of ethanol at a particular fixed temperature. The vapor pressure for pure methanol is 81 kilopascals, whereas the vapor pressure of pure ethanol is 45 kilopascals. In this case, when we want to find out the total vapor pressure, we will take into consideration there are 3 moles in the mixture. 2 of these are methanol. So the mole fraction of methanol comes out to be 2 by 3. Whereas only 1 mole for ethanol comes out to be 1 by 3. So the partial vapor pressure can be calculated for the methanol. 2 by 3 into 81 comes out to be 54 kilopascal. Whereas for the ethanol, it comes out to be 1 by 3 into 45, that is 15 kilopascal. In order to calculate the total vapor pressure, we will have to add both the components, coming out to be 69 kilopascals. We can represent this Raoult's law in a graphical representation when we try to plot the graph for both the components on the x-axis, where vapor pressure of pure B is taken on the one hand side and pure A is taken on the other hand side. You will get a straight. For a non-volatile solute, the vapor pressure, because the non-volatile solute does not vaporize it, so its own contribution is negligible. In such a case, the non-volatile solute is equal to the mole fraction of the solute in the solution. Mathematically, it can be represented as P naught minus P S upon P naught is equal to N2 upon N1 plus N2, which is xi2. Here on the left hand side, P naught represents the vapor pressure of the pure component and PS represents the vapor pressure for the solution. Here N2, N1 are actually the number of moles of the component, which actually are helpful in calculating the mole fraction. Then comes, on the basis of Raoult's law, we can actually identify that whether the solutions are ideal or non-ideal. Hence, in this case, the solutions are considered to be ideal when they follow all the conditions and components of Raoult's law under all the conditions, and they are ideal solutions when the delta H mixing comes out to be 0. Hence, there is no enthalpy change. Delta V mixing is also 0, so there is no change in the volume. And this could be because of the strong intermolecular attractive forces, which are nearly equal in the case of each component as well as when the both components are mixed together. The example of such type of solutions are benzene and toluene when mixed together, hexane and heptane when mixed together. Same way, the non-ideal solutions are those solutions which do not obey the Raoult's law. Hence, they are considered as non-ideal solutions. Their delta H mixing can be greater than 0 and their volume can also be greater than 0. The common example for these are ethanol and acetone. Carbon disulfide and acetone also forms non-ideal solutions. From this topic, students, you would find reasoning questions and numericals to be expected in the board examination. Thank you, and then we'll continue the next topic in the next series.